Proving hyperbolic identities. Best way to do this is to go back to the exponential definitions. And in fact, that's what you're expected to do for the further maths course at A level. So here's an example. It's a hyperbolic identity. It is cos squared of x minus sine squared of x is always 1. You'll never be asked to prove something that isn't true. So this is a true statement. We're just going to prove it. So we're going to use the definitions for cos and sine in terms of exponential functions and show that this will always be the number 1. So we call that cos of x is, by definition, e to the x plus e to the minus x, all divided by 2. Probably should put a little colon there. By definition, that's what it equals. Sine of x, defined very similarly. That is e to the x minus e to the minus x, all divided by 2. So what I'm going to do is I'm going to take both of these definitions and I'm going to square them because I need to put the squared forms into my identity. I'm going to plug these into the left-hand side. All the e to the x's will cancel and I'll be left with a number 1 on the left, which is then a true statement. Okay, so cos of x, or cos of x squared, that's going to be equal to e to the x plus e to the minus x squared divided by 4. Okay, so squaring this, so square the top, square the bottom. Multiply out this bracket, we're going to get e to the 2x plus 2 of the cross, so that's just the number 2 because the e to the x times e to the minus x is 1. And then we're also going to get a plus e to the minus 2x. That is still all over the number 4. Something similar can be done for sine. So sine squared of x is going to be e to the x minus e to the minus x squared, all over 4. Again, multiply out the numerator. We're going to get e to the 2x. I'm going to get a minus here, and then a plus again e to the minus 2x, and that's still all over the number 4. And now look at the original identity. We want to take the cos squared of x and subtract the sine squared of x. We're going to take this expression and we're going to subtract this expression. So this tells us that cos squared minus sine squared is equal to e to the 2x plus 2 plus e to the minus 2x minus e to the 2x minus 2 plus e to the minus 2x, all divided by 4. Okay, so this first part is cos squared, the second part is sine squared, and I'm subtracting the latter from the former. Because it's a show that question, i.e. the answer is in the question, just be a little bit careful with how much detail you put down in your answer. So I'm just going to write another line here, which I wouldn't normally do, which is to multiply out essentially this bracket. So I'm going to e to the 2x minus e to the 2x. Then I'm going to get plus 2 minus minus 2. I'm going to get plus e to the minus 2x and then minus e to the minus 2x. That's an additional line of working just to convince the marker or the examiner that you know exactly what you are talking about and how this is indeed a correct statement, a correct identity. Those two cancel. Those two cancel, those two combine, so that's 4 over 4, which is 1. So cos squared minus sine squared is 1 for all values of x. Cos squared of x minus sine squared of x equals 1 for all x. Okay, because what happened was all the e to the x's here cancelled. So we're left with an expression which doesn't contain an x. It doesn't vary with x. It doesn't change with x. So therefore, this is 1 for all values of x, which is then the identity. So therefore, h in there. Cos squared of x minus sine squared of x is always 1. There we go. All right, so that's the first one. Let's have a look at a similar example. This is a double angle one. Double angle. So what we're going to do here is we're going to do exactly the same thing. Plug in our definitions for sine and cosh, and in this case sine of 2x, and show that these are always the same. Okay, I'm going to work both left and right at the same time and then conclude that they are the same. If you want to have a go at this before I reveal the answer, then pause the video now. Okay, so if you had a go and you got it, well done. But I'm going to go through the solution. So we've got 3 definitions of hyperbolic functions here, so I'm just going to write them all down. So sine of x, by definition, is e to the x minus e to the minus x over 2. Cosh of x is e to the x plus e to the minus x over 2. And we also need sine of 2x, which is e to the 2x minus e to the minus 2x over 2. Okay, so same definition as sine, except because the input is x, is now 2x, we're going to replace the x with a 2x. Simple as that. Okay, so the left-hand side then is equal to e to the 2x minus e to the minus 2x all over 2. At the right-hand side is the product of those times 2. So the right-hand side is 2 times sine of x, which is e to the x minus e to the minus x over 2, times the cosine of x, which is e to the x plus e to the minus x, all divided by 2. Okay, so let's multiply out this bracket. 2 times 2 divided by 2 times 2 is a half. And then multiplying out this bracket, we're going to get e to the x times e to the x is e to the 2x. I'm going to put the cross terms in, even though they cancel, just because it's a show that question. So e to the x times e to the minus x is 1. E to the minus e to the minus x times e to the x is minus 1. And then I've got that times that, which is minus e to the minus 2x. Okay. So I'm just showing in a little bit extra detail how this gets to this, okay? Just to convince the examiner that I know what I'm doing. The ones cancel, so we're left with a half e to the 2x minus e to the minus 2x, which is, of course, the same as e to the 2x minus e to the minus 2x, all divided by 2, which equals the left-hand side. Okay, so the definition there. So once you've got a right-hand side is identical to a left-hand side for all values of x, then we can conclude then that the identity is true. Okay, this is true for all x. Okay. All right. So that's all the examples I wanted to do, but I did want to compare the hyperbolic identities with trigonometric identities. This is not something you need to know for this course, but I thought it would be interesting to kind of point them out anyway. There's some subtle differences between the trig identities and the hyperbolic identities, and there's a general rule of thumb which allows us to state the hyperbolic identity from a trig identity. You do not need to know this for this course, and if you're asked to prove an identity, you still need to go back to the exponential definitions to do so. Okay, but I thought I'd include this because it's interesting. So we've got 3 trig identities which are from the Pythagorean theorem. The standard one you learn in year 12 is cos squared of theta plus sine squared of theta is 1. In fact, I think you learned that before year 12. And then we have the 2 from year 13, which are taking these and dividing by cos squared or sine squared. Okay, so these are 3 trigonometric identities that you need to know for the A level in maths. The hyperbolic functions have equivalents, except there is just a change of sign. So the positive is changed to a negative in all 3 of these locations. Okay, so it's cos squared minus sine squared, which is the one I proved first. You can also prove 1 minus than squared of x is sec squared of x. And you can also prove that coth squared of x minus 1 is cosec squared of x. Okay. Compound angles, I couldn't quite fit these on next to each other, so they've gone down a line. But compound is when you add 2 angles together, and they are pretty much equivalent to the trig ones, hyperbolic ones, trig ones, except there's a change here. So the sine of A plus or minus B is actually completely equivalent. So sine just gets swapped out for shine, and cosh gets swapped out for cosh in all cases, and all places that we see it. This cosh one is slightly different though. We got cosh of A times cosh of B minus or plus sine of A times sine of B, but in the hyperbolic one that changes to plus minus. And then the tan one, again, very similar. It's plus or minus on top, okay, plus, and then, but this one here, we've got a minus. What was a minus is now a plus, what was a plus is now a minus. Let's change sign there. Double angles, again, very similar, except we've got a change of sign here in the tan one. So go from tan to than. We've got a negative to positive on the denominator, and then the cos has changed sign here, here, and here as well. Oh no, that's not changed sign. Here and here, those two have changed sign. And then the three reciprocal definitions are the same. Okay, that's how they're defined as functions. Okay, so the general rule of thumb to go from a trig identity to a hyperbolic identity is if ever you've got a sine times a sine, or a tan times a sine, or a tan times a tan, which technically a tan contains a sine. So if ever you see a sine times a sine, then the sign changes. So here we've got a sine times a sine, so the sign changed. Coses don't. So cos times a cos, the sign doesn't change. There's a sine within the tan, so that changed sign. And then there's essentially there's a sine in the cot and the cosec. So those would both change sign, but it's easy to just change that one instead. Here you haven't got a sine times a sine, so that's why nothing changed. It's gone. You got a sine times a cos and a cos times a sine, so nothing changed going from the trig to the hyperbolic. Whereas with the cos one, we had a sine times a sine, so that had to change sign. Okay, so minus plus became plus minus. And then similarly with the tan, the numerator is a tan plus a tan, so there's not two sines times together, but the denominator contained a tan times a tan, which is a sine times a sine wrapped up in there, so that changed the sign. And then the same is all true for the double angles as well. Okay, no product of signs there, so nothing changes. Product of sign in the denominator there, so that changed from negative to positive. Product of signs there, so that changed to positive. Product of signs there, so that changed to positive. And then there's no products of signs in these definitions. Okay, so that is it for identities. There's quite a few questions out there. You can prove any of these hyperbolic ones using the exponential definitions, and I encourage you to do so as practice. Thank you very much for watching, and my next video will be on solving hyperbolic equations.